What's happening? All right, so let's go ahead and get into it. So we're going to pick up where we left off last time. We're going to talk about gated latches. Make sure my little pin works. Okay. So just before we talk about gated latches necessarily, let's go back and take a look at our SR latch, right? One of the things that we know the way this works is by, if we set S equal to, 1, that sort of passes a 0, which passes a 1 through there, right? And we have to sort of toggle, between S equals 1 and R equals 1. Sorry, I'm trying to do this right on the slide business. It's not going to be conducive to making mistakes. Okay. All right, so we just sort of toggle between S equals 1 and R equals 0, and S equals 0 and R equals 1. Now, the problem with that is that there's a lot that can happen in the time while these things are hanging out, right? And we're supposed to have, no change happen when we have both of them equal to 0, right? That's supposed to be no change. But glitches can happen, right? Signals, stray, like cosmic, ray can strike the device and cause it to trigger a 1 or something like that. Weird stuff can happen that can cause glitches, and so what we need to do is have some sort of way to control. Oh, is this gonna be a thing? Yeah, some way to control when the latch can switch over. So that brings us to gated latch. So a gated latch, by definition here, is a latch which has an additional input called the gate, or sometimes we call it the enable input, right? We're going to say that when the gate is in some state or when the enable is in some state, then the latch can change. So the most simple example of this, the one we're going to look at in this class, is called the NAND gated SR latch. So notice a couple things right off the bat. First off, that these things are all switched to NAND gates, right? We had NOR gates before, but now we have NAND gates. And now we have the additional signal of this G, which stands for the gate or the enable. And as we're going to see, that this gate and this extra row of NAND gates is going to sort of block the SR signal and make it so that the state in Q only updates when G is equal to 1. So let's take a look at a couple things. First off, the characteristic equation for our NAND gated SR latch is this. Q plus is equal to S and G, or Q and R prime or G prime. And our P equation is Q prime or R and G. You don't really need to know so much how these are derived. You just need to know what they are. So let's take a look at the behavior of our NAND gated SR latch. I apologize. So at the end of last class, and I didn't know the answer off the top of my head, we asked why are some of these circled? And the answer is that those are stable. You'll notice that all the ones that are circled are where the present state and the updated one don't change. So if we look at this, we've got our present state on the left-hand side. We're looking at our next state. And we have the cases where G equals 0 and where G equals 1. And notice that when G equals 0, the next state doesn't change, right? It's always stable and never updates. It's only when G equals 1 will the state update. So when G equals 1, we have a basic SR latch, right? So we'll say here at G equals 1, this is the normal SR latch. And everything behaves the same, right? So when S and R are 0, everything stays the same. Everything is stable. When S and R is 0 and 1, right, that's going to be the reset state. Everything is going to go to 0. So no matter what the present state is, we're going to get zeros in the output. SR11 is still our bad state. It's still our undesirable state. That's going to drive everything to 1, which is bad. And then our other state, SR is equal to 1, 0, is our set state. It's going to drive the next state to 1, regardless of what the present state was. So the take-home here, the exam sort of vocab question is, in a gated SR latch, when G is equal to 0, the next state doesn't change. The next state is equal to the present state. And when G is equal to 1, then it behaves exactly like a regular non-gated SR latch. And so we can define, well, there we go. Those are 2 equations for that we already talked about. Are there any questions about this latch? All right. So one last thing we need to talk about is gated latches are not without their problems. And one of the issues they have are this thing called a race condition. They used to be rather not politically correctly called race wars, but now we call them race conditions because that's a little bit more PC. But basically what happens is, imagine that just like in the SR latch, when we have everything set equal to 1, right, bad stuff happens. So here in this scenario, everything is set to 1, including G, which is set to 1. Now when everything is set to 1, we get zeros on the outputs of the first layer of NAND gates, which of course are going to lead us to 1s on the output of the second layer of NAND gates. So it's going to behave like a regular SR latch. But if we switch G just to 0, then what happens is both the S and R signals sort of race to update the state first, just like we saw in the regular latch. And which one wins comes down to just the timing delay in the individual logic gates themselves. So it's unpredictable what the output is going to be. So a race condition is when, so like when S and R are both equal to 1, as G switches from 0 to 1, both S and R will race to update the state of the latch. That output is unpredictable. And our definition here, a race condition, is in a gated latch when both S and R attempt to alter the state of Q output simultaneously, when they're both racing to try to be the first to set what Q is going to be. And the output comes down to sort of quirks of the physics of the logic gates and what the propagations delay are. So for us as engineers, we consider this outcome to be unpredictable. So that is a race condition. And it's a condition that's common to a lot of logic devices, but it's particularly bad in gated latches. To address some of these concerns, they devised this thing called the gated D latch. It's a solution to race conditions in gated SR latches. The D latch is also called a transparent latch because what happens is the Q output is equal to D for an active G input. So it looks like this. Basically, we've taken, instead of having S and R tied in to these gates, instead we have just a D output. And notice that we're going into regular AND gates instead of NAND gates. But the idea here is pretty simple, that by tying D through an inverter, it's going to force S and R to always be the complement of each other. We don't provide separate inputs for S and R. We tie one, we call it D, and we send its inverse, or what should be its inverse, what should be R, through an inverter into the circuit. So if we come over here to our timing diagram, right, as G is equal to 0, then nothing changes, right? Q doesn't update at all, but when G goes to 1, right, and that latch is enabled, then Q is just whatever D is minus just a little bit of delay, right? A little bit of that propagation delay on either side. So this is why we call it a transparent latch, right? Because it's basically just, it's transparent. Whatever is a D is going to show up at Q. And this right here is our basic form for storing a single bit of memory, right? If D is our one bit that we want to store, right, this gated D latch is a pretty easy way to just store that one bit of information. Any questions about the structure of the gated D latch or the timing diagram? All right, we'll keep moving. Let's take a look at its characteristic equation. So we can derive it using the truth table, right? When G is equal to 0, then it doesn't matter, right? Q is going to be whatever the present state was, or Q plus is going to be whatever the present state was. And then when G is equal to 1, Q is going to be whatever D was. Let's see. Let's sort of work on that a little bit. So if we were to lay out the minterm expansion, we would say that Q is equal to the sum of minterms. What, 1, 3, 5, no, excuse me, 6, and 7.
Is it not just kind of like a month?
Say it again?
It's just like when you have the...
David, I'm sorry, your mic is all garbled up, even more so than normal.
Is it not just a mux with G as control, D and Q as the inputs?
I mean, you could think of it as that. I mean, that's not directly what it is, but you could, yeah, you could think of it that way. The implementation, the logic circuit, isn't quite the same. The question was, isn't this basically just a multiplexer? And the answer is, yeah, this is basically just a 2-to-1 multiplexer. And in fact, the equation is about the same, right? Our characteristic equation here is, you know, if it's G is equal to 0, then it's Q. If G is equal to 1, then it's D, right? So you're right. This is basically just a 2-to-1 mux with a slightly different logic implementation. And you could use this gated latch as a mux if you wanted to. All right. Let's see. Any questions about this slide? All right, so that is the end of what we were talking about last time. Last time we sort of talked about feedback in our switching circuits, talked about set reset latches, talked about deriving the characteristic equation, and here we just looked at gated latches. So, any questions about anything from that first lecture? And don't forget, I'll throw up these slides as PDFs on Blackboard. Okay. So let's lose that. Now, today's lecture. We're going to talk about edge-triggered flip-flops. Just to give a quick overview, we're going to talk about edge-triggered D flip-flops, which is the most common type of flip-flop. We'll talk about calculating the minimum clock period of a flip-flop circuit, right? How fast can we clock flip-flop? And then we'll look at SR flip-flops and JK flip-flops. The book talks about a few extra types of flip-flops, but they're a little bit esoteric, and since we're kind of crunched for time, we're not going to worry about those. They're not as commonly used as some others.
And yes, the D has used regular AND gates, not an AND gate. Went out to that in the chat.
Wait, hold on. Say that again? Oh, I was looking at the wrong chat.
Question in the chat.
Sorry, Cody. I was over in the other. I was looking in the wrong chat. Yeah, it's using AND gates and not NAND gates. No problem. Thanks, Devin, for catching that. I was in the chat for my next class by accident. Okay, so let's take a look at edge-triggered D flip-flops. Okay, so we won't spend a ton of, well, that's not true, actually. Before we dig into the internals, we'll sort of take a look at the sort of basic structure. The edge-triggered D flip-flop has a lot in common with that gated D latch. In fact, a lot of the inputs are the same. We have a D input, we have a Q output, we have an IQ output, and then it's also transparent, right? So when, you know, D is equal to 0, the output is 0. When D is equal to 1, the output is 1, regardless of what the last state was. So we have our characteristic equation here is Q plus is equal to D. You know, that's pretty easy to prove with some Boolean algebra, right? Since it's just, what, 2 and 3. So we'd say D and Q prime, or D and Q, which simplifies to D. And there's two types that we're going to focus on. There's what's called the rising edge trigger, and there's what's called the falling edge trigger. Now, the signal here, notice that we've kind of changed the symbol to have this little triangle built into it. Anytime you see that, that's going to be a clock signal. A clock signal. And a clock signal is just a square wave that's going to drive the flip-flop. This lets us keep everything in sync with each other. Now, there's no inverter, no inverting dot on this left-hand one. This means it's a rising edge trigger. And when you see the dot, that indicates that it's what's called a falling edge triggered D flip-flop. The output, the relationship between Q and D, the characteristic equation, never changes regardless of whether or not it's a rising edge or a falling edge triggered flip-flop, but it does affect the timing diagram. A couple of definitions here. A rising edge is when the clock signal transitions from 0 to 1. You know, that's when we go from 0 to 1. That's a rising edge. We also sometimes, in fact, probably more commonly, we refer to this as a positive edge triggered flip-flop. A falling edge is when the clock signal transitions from 1 to 0. And we also call this a negative edge triggered flip-flop. And so the bubble on the clock input indicates a falling edge trigger. Like I said, if you see the bubble on the triangle, that indicates a falling edge triggered flip-flop. And that's going to be true for any of the flip-flops that we look at, the JK or the SR flip-flop. So those are some definitions. Let's take a look at a timing diagram. Now, specifically what we're looking at here is that negative or falling edge trigger. So let's take a look. So we've got our clock signal just sort of pulsing along. And then notice that when the clock signal falls, it goes from 1 to 0. That's when things sort of kick off, right? So whatever the value of D, whatever state D is in at the moment that the clock signal triggers, right? When the active, what they call the active edge occurs, right? That's what's going to update the state. So because D was 1 when the falling edge happened, Q, our output, minus some delay, is going to go to 1, right? And same deal on this next one, right? Nothing happens on the rising edge. Notice that nothing happens on top. This is the difference between a flip-flop and a latch, right? A latch would trigger, it would switch, it would update its state here while clock was equal to 1, but a flip-flop only triggers when that falling edge occurs, when that active edge happens. So again here, when this falling edge happens, D is sitting at 0. So Q, minus some propagation delay, will drop to 0. And then same thing for the next falling edge. D was at 1, so Q goes to 1. Cody asks, why is it not triggered for every falling edge? I'm going to guess that you're referring to this one. It is triggered. At this one, it is. The falling edge happens. D is at 1. Q was at 0. Oh, come on. And then it goes to 1. The one before that. But D doesn't change value. So D doesn't change. Yeah, D is not the one that changed, right? D, remember, is the input. And Q is the output. So Q changes. Q is the one that updates on the falling edge, not D, right? whenever the falling edge occurs, Q looks to D and says, all right, you were 1, so I'm going to switch to 1. Or you were 0, so I'm going to switch to 0. Is that what was happening? Were you thinking D should be switching? Yeah. No, that's common. Really easy mistake to make. Oh, yeah. I thought that simply D switched every value every time the falling edge occurred. No, D is the input. D is what we control. D is the bit that we want to store. And Q is what is driven by the clock. So some other things can happen. So let's say, you know, here at this very last one, D goes from 0 to 1 and then back to 0 again. But it doesn't, there's no falling edge that occurs during that time. So there's no, Q never goes to 1 at any point during that time, right? So Q has to be whatever the value of D is at the time the active trigger happens, that's where Q is going. All right. After we spent so much time unpacking this, are there any questions about this timing diagram? Like I said, the big take home is on the falling edge, if it's a, and you'll be told, you know, I'll specify if it's a falling edge or a positive edge triggered flip-flop. And so whatever the active edge is, whatever D is, that's what goes to Q. That's the important sort of take home principle there. All right, let's take a look at the structure. The structure is actually pretty simple. There are two regular sort of, not SR. So these are two gated D latches. Attached in series. And then we just have a clock signal that drives both of them together. D goes into the first one. And the magic happens here with this inverter. So this inverter here keeps the latches always sort of out of step with each other. So essentially what's going to happen, we'll take a look at the timing diagram next. But what happens is on, you know, sort of when the clock is in one state, whatever value gets loaded into the first latch, and then when they toggle to the next one, it gets passed to the next latch. So this inverter causes this sort of, and actually this is where the name comes from, the sort of flip-flop effect. As the clock triggers, we flip-flop the values between the two separate latches there. So remember these annotations, because we're going to look at the timing diagram here in a second. G1 is the gate for the first latch. G2 is the gate for the second latch. D1, Q1, so on and so forth. So let's look here at this timing diagram. So this is the clock. Remember, the clock is tied directly to the gate of the first latch. So that's what we're going to look at first. So we have this long sort of clock cycle. We've got D input. So 1, we'll think of P as input to the second latch. And yeah, so we're hanging out here, and let's see, G2 is equal to 0, which means that Q is the Q latch, the final latch is never going to change, so Q stays the same. But if G2 is 0, then G1 is 1. So that first gate of the first latch is set at 1, which means our first latch is going to be transparent. That whatever D is, its output is going to be exactly that, of course, minus some propagation delay, right? So those values, so whatever the last value is here, right, before the switch happens, we look and see, all right, well, what was the value of D? That's going to be the value of Q. And now the switch happens there, boom. And remember, because it's a latch, that value at P is locked in, right? It was 1. Now its signal has gone to 0, so everything stays the same. And now we're looking here, G2, the gate, the enable of the first latch is set at 1, and that's what the second latch, that's what Q is going to pick up on. Oh, come on. Cooperate. Just like that. So when clock goes to 1, this is when it flips over, and the value that was originally a D gets dumped into Q, and that, of course, isn't going to change until the clock drops down to 0, which means that we're now going to pick up on the first latch and pick up whatever its value of D is. In this case, it gets left at 0. Stop. Right? And because that's what happens when the edge happens, when the active edge occurs, then Q goes to 0. So here's my question for you guys. What type of trigger does this clock use, or does this flip-flop use?
Falling edge.
All right, we got falling edge. Does anyone think it's positive or rising edge? Nathan thinks it's rising. Colby thinks it's rising. Nathan and Colby, why do you think it's rising? Don't all jump up at once. Right, yeah, you're exactly right. So this is a rising edge flip-flop because don't forget, we're making a reference to what the clock does. And so it says, you got to ask, well, on what edge of the clock is Q updating? And in both cases here, looking at just this timing diagram, Q updates when clock goes from 0 to 1. Which means that this is a rising edge clock. So, for example, on a test, I might show you a timing diagram like this one and ask you, is this a rising or a falling edge flip-flop? And like I said, you got to look and see, where is the output? Where is Q updating? And is that when the clock goes from 0 to 1, or is that when the clock goes from 1 to 0? All right. That's enough for about the edge-triggered D flip-flop. Before we move on to the next topic, are there any other questions about this flip-flop or the whole concept of edge triggering altogether? G1 in this diagram was this. It's the input, the gate input to the first latch. All right? And because it's passed through this inverter, it's going to be the opposite of whatever the clock signal is. No, G1 is not itself the clock, right? And sort of arguably neither is G2, but because G2 isn't inverted, right? It's tied directly to the clock signal. Because it's tied directly, we say that G2 is equal to the clock. So that's why that's why we've got this statement here that says clock equals G2, but not for G1. What is happening with P? P is the step in the middle, right? P is the output of the first flip-flop, right? It's the Q output of our first latch. I think I accidentally just called it the flip-flop, but it's our output of the first latch. And so if we look here, notice that when G2, when the clock is 0, G1, the gate of the first latch, is equal to 1, which means that P is going to transparently do whatever the D input does. So P is the output of latch 1. So it is corresponding to D, but with G1 as the clock. Yes, but don't use the word clock because it's a little bit dangerous. So it corresponds to D, but with G1 as the enable. Because we're only looking at just that specific latch there. Yeah, I know it gets a little confusing because we're sort of using the term enable and clock kind of weirdly interchangeably. But just think of enable is what happens at the latches, right? The actual enable signal for the latches themselves, right? Clock is the signal that gets passed to the flip-flop as a whole. And then weird stuff happens to the clock once it's inside the flip-flop. All right. Let us keep it going. So next up, let's talk about minimum clock period. It's sort of an interesting topic, and it's got a few sort of important details. Now, here, if we look at a much simpler timing diagram for our edge trigger D flip-flop, we've got our D input, we've got our clock, and we've got our Q output. And then we've got D is 0 for a long time, and then it sort of jumps to 1 for a long time, and it jumps to 0 and back and forth. And then this is also going to be a rising edge triggered flip-flop. And the thing that we need to sort of drill down on is what happens right here. Because it's not, before we said that it's whenever the clock changes, whatever the value of D is at that time, that's going to be the value that gets passed to Q. And the reality is that that's not necessarily the case. There's some time on either side of the edge that D needs to maintain that value in order for the transition to occur. And there are two components to this. There's the first part, what we call the setup time. So the setup time is the amount of time that D must be stable before the active edge, right? For a rising or falling edge, there's some amount of time that D needs to be just sitting in one place and be stable before the rising edge occurs. And then there's also some amount of time after the rising edge occurs that it still needs to remain stable. We call that the hold time. Our definition down here is hold time is the amount of time that D must be stable active after the active edge. So the thing to memorize there is setup is time before the active edge, and hold time is time after the active edge. And don't forget, we also have some propagation delay in Q, and hold time is almost always about the same as the propagation time. So the amount of time that you have to hold on here is going to be about the same as the delay. So you have to hold D stable until Q flips, and then you're good to go. So they're going to be about equal to each other. So we use these kind of interchangeably in our calculation. So let's sort of game it out a little bit. Let's say we have a really simple oscillator. An oscillator, right? This is that inverter feedback loop, but we're throwing a flip-flop in the mix, right? So that signal, that inverting signal, that oscillating signal is going to sort of pass around from the inputs to the flip-flop. And let's go ahead and put some basic parameters on this. We'll say that the inverter delay, so the time delay inside the inverter, is 2 nanoseconds. The delay in the flip-flop itself is 5 nanoseconds. The flip-flop has a setup time of 3 nanoseconds. And let's say that the clock, for the purposes of this example, is clocking at 9 nanoseconds. So inverter delay is 2 nanoseconds. Flip-flop delay is 5 nanoseconds. Setup time is 3 nanoseconds. And clock period is 9 nanoseconds. So let's go over to this example. Let me jot down our parameters here. Remember, we had 2 nanoseconds. We had 5 nanoseconds. Our clock is running at a period of 9 nanoseconds. And what was the last thing we had? Oh, we said setup time. So T sub SU is equal to 3 nanoseconds. So now here, let's look at the clock. Let's say that well, we have a rising edge here, then we have a falling edge. Let's see, what is... Okay, let me take a step back. So Q is originally at 1, D is originally at 0. It looks like from... oh, no. Okay, so it wants to trigger on... So D is originally at 0. Q is original 1. Sorry, like I did this yesterday and I didn't look too closely at it, so I was got to catch myself up. So D is 0, Q is 1. The active edge is the rising edge, which means that Q now wants to go to 0. So the flip-flop itself has a delay of 5 nanoseconds. So we got to wait for 1, 2, 3, 4, 5 nanoseconds before Q will flip over. Now, from the time that Q flips over, we're sort of off to the races here, right? So that 0 is going to swing around, and it's going to take it another 2 nanoseconds, right? So 0 ends up here, which means a 1 is going to happen here, but it's going to take 2 nanoseconds to get there, which means that we got to wait another 1, 2 nanoseconds before D is going to update. But remember, our clock period is 9 nanoseconds. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 nanoseconds before the next rising edge. And our setup time is 3 nanoseconds, which means we have to go from 9, minus 1, minus 2, minus 3. So here is the place where D has to be stable before... or D has to be stable at this point when at 3 nanoseconds before the rising edge of the clock. Otherwise, Q won't update. So Q won't go back to 1. I know that was a lot, so let's kind of go back and unpack that just a little bit. So there's 9 nanoseconds of time between these, which means that with a setup time of 3 nanoseconds, you actually have, 5 nanoseconds? No, what am I saying? Math. 7. No, 6. Stupid. Can't do math, which means you actually have 1, 2, 3, 4, 5, 6 nanoseconds to oscillate, right? You've got 6 nanoseconds to get the 0 back out, pass it around, and then get it back into the input of the gate. So the question here is, or I guess it's not really a question so much as the answer here is, with a clock period of 9 nanoseconds, this is not fast enough to oscillate. So it's not going to pick up the signals. This is going to kind of sit there and not really do anything. The clock is going too fast. The period is too slow. So, any questions about that before we move on to a different, or we're going to expand the clock period just a little bit? I know that's kind of weird. Cody, did you have a question? I saw you typing. Yeah. All right. So let's make the clock period a little bit larger, right? So let's blow it out, and let's say that we have a clock period of 15 nanoseconds. So that means that we've got 15 nanoseconds from the time the clock triggers, which means when we account for setup time, that means we have what? 14, 13, 12 seconds. 12 nanoseconds to oscillate. So 12 nanoseconds to oscillate. Now, once we get a value at, let's say, 0 here, remember it's going to take 5 seconds for the delay. The inverter is another 2 seconds, which means it takes 7 seconds to get the job done. But we have 12 seconds, which means we have 5 nanoseconds of extra time. So we actually can get it done in that amount of time, but we've got some extra left over. We're not as optimized as we can possibly be. So the question is, well, what is the minimum value that it's going to be at? And it turns out that in this case, it's 10 nanoseconds because it takes 7 nanoseconds to do the job. And we've got to get it done in 3 nanoseconds before the end of the clock pulse, right? Because we have to be there in time for the setup time. So that means a minimum clock period of 10 nanoseconds is what's required here. But to generalize it out, minimum clock period is this equation, right? Minimum clock period is equal to the propagation delay, right? In this case, it's the time it takes to do everything. So that would say, we would say that T prop is equal to the time in the inverter plus the time in the flip-flop, right? Whatever, or if you have any other additional circuitry going on, whatever, however long it takes to add up all those propagation delays, plus the setup time for the flip-flop gives us our, so T is equal to T prop plus T setup. So that's how we calculate our minimum clock period. Any questions about that? Okay, all right, let's move on. And we're going to kind of quickly go through these two other types of flip-flops just so that you're aware of their existence and kind of have some basic sense of their behavior. And the first one we're going to talk about is the SR flip-flop. So the SR flip-flop basically says, let's do, it's the SR latch but on an edge. Right? So it's going to have the exact same concepts, right? When S and R are both equal to 0, the state doesn't change, right? When S is 1 and R is 0, the state Q goes to 1. But it's going to happen after an active clock edge instead of just whenever, you know, all the time, or just whenever there's a gate, right? Only on the active edge. And same deal, S equals 0, R equals 1 is going to bring us to Q equals 0, again, after an active clock edge. And then SR, S equals R equals 1 is not allowed, but it will let you do it. It'll give you that sort of race condition invalid state. Any questions about that as a concept? Okay, all right. Here's the structure. Again, you don't need to be able to break it down. You just need to kind of be able to recognize it. If I show you a picture of it on the test. And you can think of it as it's basically two gated SR latches. Again, notice the presence, the lack of NAND gateness. So two gated SR latches sort of stacked together with that inverter that makes it a clock. So when you have two, so if S and R, AND gate, you can think of this as the G1. And notice here that it passes again into those AND gates. Think of that as the G2 for the second SR latch. And that's basically the structure there. So, any questions about the structure? Again, the important thing here for me, as far as an exam goes, is, you know, recognize that this is what the SR flip-flop looks like. So if I show you the picture, you can say, oh yeah, that's the SR flip-flop. No, there's not. I really wish there was. I recognize that this is a very not woke way to name things anymore, but don't forget, a lot of these terms were developed in like the 1940s and 50s. So yeah, master and slave is a pretty unfortunate title. I mean, they call it that because this one sort of drives the next one. I'm sure someone has come up with a better terminology. It just hasn't made its way into the college textbooks yet. All right, so let's see. So here's the timing diagram. We're almost out of time, so we won't dive into this. But feel free, obviously, feel free to take a look at it. And if you have any questions about it, come and ask me. But like I said, it's going to be the same behavior that you expect from an SR type circuit. Things are just going to happen on the edges, though, instead of on some kind of enable signal. So that's the SR flip-flop. Let's quickly go over the JK flip-flop. JK flip-flop looks like this, but it's got some pretty interesting behavior, most notably that, let's see, if J is equal to 0, then Q is going to be, well, I take that back. Let me bounce back from that. And let's just take it one at a time. So if it's all 0, then the state stays the same. So in the case of JK equals 0, 0, then Q naught just passes directly. Kind of like the SR latch, nothing really happens. When JK is equal to 0, 1, right, you can think of this as being the, we could write S and R up above this, right? So this is going to be the reset state. So no matter what present state is, we're going to go to 0, and same thing for 1, 0, right? In this case, regardless of what the present state is, it's like the set state, but it's going to go to 1. What makes the JK flip-flop different from the SR flip-flop is what you do with the 1, 1 case, right? In the 1, 1 case, on an SR flip-flop, it says, or an SR latch, it says that everything dies, right? The system explodes, it all melts down. Bad things happen. Please don't ever make S and R equal to 1. The JK flip-flop says, well, I don't know, man. Let's make it such that when we have 1, 1, let's just invert the cases, right? So when you have a 1, 1 on the JK flip-flop, you're instead going to toggle the state. So this is, so a test question asks, what is the difference between a JK flip-flop and an SR flip-flop? It's that the JK flip-flop toggles the next state for JK equals 1, 1. That's the primary difference between the SR and the JK flip-flop. And here's what its structure looks like. Again, it looks an awful lot like the SR latch. The only difference is that these first layer of AND gates is cross-coupled with a feedback loop. So Q naught goes to the top, and Q feeds back around to the bottom. So by providing that feedback loop, you're able to achieve that state where when J and K are equal to 1, you're going to toggle the state. So there we go, man. It is 12:50. Let's see, flip-flops. Yeah, I meant to take that slide out. And there we go. So that was a lot. We went pretty fast today. We went through those gated latches, and we went through all of these different types of flip-flops. The important take-home messages there are, be able to calculate the minimum clock period if I give you these parameters. Be able to sort of work through the edge trigger D flip-flop timing diagram, since that's the most common one. I'm going to make these into PDFs, and I'll put these on Blackboard for you. Yeah. And then for the other two, for the SR and the JK flip-flop, be able to sort of describe their operation, but more importantly, just be able to sort of pick them out of a crowd. Oh, it is. Yeah, it's 11:50. My clock here is messed up. So yeah, 11:50. So yeah, for SR and JK flip-flops, just be able to recognize them. If I show you, the diagram, say, that's JK, that's, SR. And obviously, of course, I would remove the, S and the R from the output. All right. Any other questions about any of this stuff? Cool beans. In that case, we will pick, let's see, Nathan asks, gated SR flip-flop only allows change on the clock pulse. Right, or yeah, so on the rising, or the falling edge, on the active edge of the clock. That's what makes a flip-flop different from a latch. And in fact, you can't really have a gated SR flip-flop. You have a gated SR latch that only changes on the input pulse, but an SR flip-flop changes on the edge. And that's really, I mean, honestly, that's really kind of the difference in terminology there, is if it, you know, if it changes like on, you know, it equals 1, then it's a gate. If it changes on the edge, it's a clock. It's really kind of a way to look at it. All right. Thank you so much, guys.